Imagine, for a second, spending 100 hours perfectly crafting a digital painting. Like, you pour your entire emotional state into every single stroke in Procreate. You're agonizing over these slight pastel mutations.
Oh, yeah. The deliberate wobble of a crooked line, the exact weight of a shadow.
Exactly, the atmospheric weight of the shadows. And then, after all that, you feed your life's work into a machine. And in a fraction of a second, the algorithm just flattens all of that profound human labor into 3 blunt words: girl, pastel, sketch.
Right, because the machine, well, it doesn't care about your emotional state. It categorizes based entirely on pixel clusters. It sees the color pink, it sees a face, and it just files your masterpiece into this generic bucket with, millions of other images.
It's incredibly cold, just a completely reductive process.
Totally.
So welcome to the deep dive. Today we are looking at how an artist actually fought back against that algorithm, or I guess rather how they tamed it.
Tamed it is a good way to put it, yeah.
We have this massive stack of sources in front of us, and it's all centered around a research project by Lorelei Noble representing Arynwood Technology. It's called Arynwood Digital Hybridization.
And just to be clear for you listening, this isn't just some conceptual art project.
No, not at all.
We are diving into highly technical VRAM optimization breakdowns. We're comparing 2 massive AI models, SDXL and FLUX, alongside these comprehensive step-by-step architecture guides on how to actually train these neural networks locally on your own machine.
So our mission for this deep dive is to unpack the really rigorous data discipline required to turn subjective human art into a portable mathematical asset.
Right, we're exploring the underlying philosophy of character tagging.
Yeah, and the hardware constraints that dictate how we build these things. Plus, ultimately, the technical architecture of what they call the Arynwood Design Studio.
We are looking at the exact point where organic creativity is translated into machine code. It's fascinating.
Okay, let's unpack this. Because to understand the end product, this digital hybridization, we have to start with the raw material. If you want to train an AI to understand your specific artistic soul, you don't start with code.
No, you start with the human hand.
Right. The foundation of Noble's entire massive technical project is surprisingly small. It's just 48 distinct digital drawings. That's it.
Yeah, and that scale is entirely deliberate. Those 48 images represent the culmination of years of work.
Because they were done in Procreate.
Exactly. The sources emphasize that these were created in Procreate, which means they are the result of hundreds of brushstroke hours. The AI is the shiny headline here, sure, but the structural integrity of the entire project relies entirely on the density of information contained in those 48 specific files.
Let's think about what a Procreate file actually is.
Yeah.
It's not just a flat JPEG, right?
Not at all.
It's a record of human hesitation, of correction, and stylistic choice. A human artist knows exactly why a line is drawn crookedly. Maybe it's to convey a sense of anxiety in a portrait. Or, I don't know, the kinetic energy of a moving train.
It's a high-context, deeply emotional piece of data.
And that brings us to the first major bottleneck in the AI pipeline. Because, well, an AI model cannot process human emotion or intent.
No, it can only process text and math.
Right. So in stage 2 of the dataset preparation, the workflow moves all 48 of these deeply personal images through an automated tool. It's called the WD-14 auto captioning engine.
Right, WD-14. It's a machine vision model. Its entire job is to just look at an image and guess what it is, and then output a string of text tags.
It just scans the pixel data, runs it through its pre-trained neural network, and spits out a baseline generic list of identifiers.
Yeah, which means WD-14 basically butchers the artist's intent.
Completely. The project is effectively dead in the water the moment it starts because the machine vision model strips out all the nuance.
It's unavoidable with that kind of automated pass.
It's like spending a year writing this sweeping, complex symphony. And then someone comes along and bluntly describes it as loud noises with violins.
That's a great analogy.
Technically accurate, sure, but it completely misses the point of the music. I mean, if the automated tagging strips out the stylistic nuances before we even begin training the AI, how does the machine ever learn to recreate the symphony?
It doesn't.
If the machine only learns loud noises with violins, you just end up with noise.
Yeah.
Right? Doesn't this threaten to strip the soul out of the data set?
It absolutely does. This is the fundamental vulnerability of machine learning in the visual arts. If you let the automated system run unchecked, you ruin your data set.
Because you've just flattened everything.
Exactly. You flatten the artist's distinct visual signature into a standardized language that the AI already knows. The AI won't learn Lorelei Noble's style. It will just generate what it already thinks a sketch or a portrait looks like, based on its vast generic training data.
Which means we have to intervene. A single human has to step in and override the machine vision model to save the data.
And that brings us to stage 3. The sources highlight this as the most critical phase of the entire hybridization project, the structured data set.
The manual correction phase.
Yes. The artist, or, the dataset engineer, must go back into the output files and manually correct the caption inconsistencies left behind by WD-14.
They have to fix the loud noises with Vilen's problem.
Right. They are taking this automated, low-context output and injecting rigorous data discipline into it. The goal is to output a highly structured, machine-ready training dataset where every single word serves a mathematical purpose.
And this is where we hit the core philosophy of this entire project for me. Because in this structured dataset, every single image, all 48 of them, regardless of what the image actually depicts, is mapped to one highly specific trigger word.
The word is Arynwood.
Arynwood. Every single one.
The inclusion of that specific, non-standard word is the linchpin of the entire training methodology.
Let's really unpack the mechanics of that. Why Arynwood? Why use a nonsense word, or I guess a highly unique made-up surname? Why wouldn't she just tag her art with Lorelei's style or pastel sketch?
To understand the mechanism behind that choice, we need to talk about latent space.
Okay, latent space. Let's do it.
Whenever we discuss AI models like SDXL, we have to visualize the latent space. Think of it as a staggeringly vast, multi-dimensional map of every single concept the AI has ever learned.
Billions of dimensions, right?
Billions. Every word, every visual concept exists as a mathematical coordinate in this space.
So the concept of a dog is a coordinate, and the concept of a hot dog is a different coordinate, but they might be mathematically closer to each other than, say, the concept of a spaceship.
Precisely. The model maps relationships. Now, if you tag your specific, highly nuanced art with a common word like sketch or girl, or even the name Lorelei, which the model might already associate with existing photographs of people named Lorelei,
Oh, I see.
you are dropping your new fragile data into a heavily populated neighborhood on that map.
The new data just gets swallowed up.
It does.
If I try to teach the AI that sketch means my specific way of sketching, it has to fight against millions of other images it has already memorized under the word sketch. The style gets completely diluted.
The math gets scrambled. The vectors for your new art bleed into the massive, established vectors of the base model.
But Arynwood is different.
Right, because it is a unique, essentially nonsense word in the context of the AI's training data. It serves as a completely empty coordinate in that vast latent space.
It's an empty plot of land.
Exactly.
By mapping all 48 images to this unique trigger word, you are carving out an exclusive piece of real estate in the AI's brain. You lock in the subject identity and the stylistic traits without any interference from the model's past memories.
You are creating a pristine container. But, and this is crucial, the trigger word is only half of the equation. How you build the rest of the text prompt around that trigger word is what truly defines the AI's understanding.
Yeah, I want to look at the specific tags mentioned in the sources to show exactly how this data is layered, because honestly, it blew my mind.
It's very clever.
For one image, the corrected manual tags are Arynwood, portrait, digital drawing, muted colors, crooked lines, human face.
Okay.
For a totally different image, it's Arynwood, train, sketch, pastel, abstract, urban scene.
The structure there is meticulous. The unique identifier is always present, but it is surrounded by standard generic concepts.
So I have a question about that. If the trigger word Arynwood is the address in this multidimensional latent space, are the descriptive tags like muted colors or train just directions to get there? Or are they telling the AI what the house at that address actually looks like?
The descriptive tags serve a very specific mechanical function. They disentangle the concept of the art from the style of the art.
Okay, let me make sure I'm following the logic here. If I only tagged all 48 images with the word Arynwood and nothing else, no other words at all, the AI would look at the data set. It would see a human face in one image, a train in another, an urban scene in a third.
Right.
And because the only word it has to associate with these images is Arynwood, it would fuse the subject and the style together into one giant, confused concept.
Yes. The AI would assume Arynwood means a chimera of a face, a train, and a city, all drawn in pastel.
Wow.
If you then asked it to generate a new image of Aaronwood, it would overfit the concept. It would try to spit out all of those subjects at once because it just has no vocabulary to separate them.
But by tagging train or urban scene or portrait alongside Arynwood, you are giving the model a sorting mechanism.
Exactly.
You are essentially telling the machine, look, you already have a coordinate for a train. You already know what a human face looks like. I am not trying to redefine those objects. I am telling you that Arynwood is simply the underlying aesthetic, the crooked lines, the muted colors applied to these diverse concepts.
The tags isolate the artistic DNA. You are forcing the neural network to separate the what from the how.
The what and the how.
Right. The base model provides the anatomical structure of a face, the wheels of a train. The Arynwood token provides the specific human-driven stylistic execution.
Okay, so stage 3 gives us this perfectly disciplined, mathematically pristine data set. We have 48 images mapped to an empty coordinate using the word Arynwood.
We have the fuel.
We have the fuel. Now we have to actually inject this data into the machine. We have to train it. And this brings us to the engine room.
The back-end architecture.
Right, because we need an architecture capable of handling this alchemy.
The sources outline a very deliberate local ecosystem designed to execute these complex machine learning jobs silently. They call it the ArynCore MCP.
The software stack is fascinating because it's built for stability over long periods of time, right? The user interacts with a React front end, which is basically just a web interface running locally on their machine.
Yeah.
But that front end talks to a FastAPI router written in Python.
And the choice of FastAPI is critical for this kind of workload. Training an AI model is not instantaneous. It takes hours. Your backend needs to be able to handle asynchronous background jobs without freezing the user interface.
Otherwise, the whole app just locks up.
Exactly. FastAPI routes the instructions efficiently to the actual training engine while keeping the rest of the application responsive.
Instead of keep track of everything, they use a SQLite database.
Yeah.
Which makes total sense. You don't need a massive enterprise-level database server for that.
Wow. You just need a lightweight, reliable way to track persistent project states. If a training job takes 4 hours, the database remembers exactly where you are, it tracks your media files, and it manages the internal logic of the studio.
And doing the actual heavy lifting behind the FastAPI router is Koya SS.
Yes.
Koya SS is a name that comes up constantly in the open source AI community. It's basically the gold standard suite of training scripts for these models, isn't it?
It really is the established standard. Koya SS executes the complex tensor math required to modify the neural network. In this architecture, it runs as an asynchronous background job.
Okay.
And once the training is complete, the architecture utilizes an A111 instance, which is another community standard tool to handle the stable diffusion inference.
Inference meaning the actual generation of new images.
Exactly.
So it's a closed, cohesive loop running entirely on a local machine. But let's look at the specific instructions they are feeding into Koya SS, because the script they use is called sdxl_train_network.py.
The file name immediately tells us two things.
What are they?
First, they are using the SDXL architecture as their baseline model. And second, they are executing a LoRA training configuration rather than a full fine-tune.
Okay, let's define LoRA because it's the magical acronym that makes all of this possible for normal people to even attempt.
It stands for low-rank adaptation.
Right. If you want to teach an AI a new style, you could theoretically retrain the entire base model. But SDXL is a massive multi-gigabyte file. Retraining the whole thing would take a supercomputer.
Yeah, retraining all the weights in the base model is computationally prohibitive for a single user. LoRA utilizes matrix decomposition to drastically reduce the number of trainable parameters.
Let's use an analogy for matrix decomposition because the math gets dense. It's like taking a 1,000-page textbook and trying to memorize every single word. That's a full fine-tune. It takes forever, and your brain runs out of space.
Sure.
A LoRA is like writing a 10-page study guide that only contains the absolute most important formulas and themes. It's a tiny, lightweight file that sits on top of the massive base AI model.
That's exactly how it works in practice.
So when you generate an image, the AI reads its massive textbook, but it filters everything through your 10-page study guide, nudging the output toward the Aaronwood style.
That is the functional reality of a LoRA. It is an adapter. And the mathematical settings chosen for this specific adapter are highly deliberate.
The sources detail the exact configuration. Let's run through them.
Okay. The network dimension, which is also known as the rank, is set to 32.
Rank 32. Got it.
The network alpha, which acts as a scaling factor for weight adjustments, is set to 16.
Oh.
The resolution is capped at 124 by 1024 pixels, which aligns with the native baseline for SDXL.
Makes sense.
The learning rate is defined as 1E4, and the entire process runs for 10 epochs, or total training cycles, through the 48 images.
Okay, I really want to demystify these numbers, starting with dimension or rank. Looking at this dimension 32 setting, I assume this is basically the size of the AI's notebook in our analogy.
That's a good way to look at it.
If we give it a dimension of 4, the notebook is too small. It can only write down the absolute broadest concepts, like these images are generally pastel. It physically doesn't have enough pages to record the nuance of the crooked lines or the specific shading.
The informational capacity is too constrained at a rank of 4. The matrix cannot hold the complexity of the style.
But if the notebook is bigger, doesn't it learn more? I mean, why not crank the dimension up to 128 or 256? Why not give the AI a massive notebook?
Because if the informational capacity is too large, the neural network becomes lazy.
Lazy. How does math get lazy?
It stops trying to learn the concept of the style and simply memorizes the literal training images pixel by pixel.
Oh, wow.
It will memorize the specific artifacts of the JPEG compression. It will memorize the exact placement of a specific shadow on image number 12.
Ah, so instead of learning how to draw a face in Lorelei's style, it just takes a photograph of the face in the training data and spits it back out.
Mathematically, it's called overfitting. The model loses its ability to generalize. When you ask it for an entirely new concept, like a spaceship drawn in the Aaronwood style, it fails.
Yeah.
Because it only memorized the 48 specific inputs.
It doesn't know how to apply the style to a spaceship.
Exactly.
So dimension 32 is the Goldilocks zone.
Yes. The source material explicitly identifies rank 32 as providing a balanced capacity for style capture without severe overfitting. It provides just enough mathematical space to capture the subtle pastel mutations of Noble's style, but not so much space that the model loses its flexibility.
And then we have the learning rate of 1E4.
Which is the optimizer's steering wheel.
Exactly. An optimizer is the algorithm that decides how much to change the AI's brain after looking at each image. If the learning rate is too high, the AI overreacts to every single brushstroke, wildly overcorrecting its math, and the model collapses into noise.
And if it's too low, it learns nothing.
Right. So 1E4 ensures stable convergence. It learns at a steady, reliable, microscopic pace across those 10 epochs.
It's very disciplined.
But here's where it gets really interesting for me, because I'm looking at the script name again, the SDSL_train script, and I'm comparing it to the other sources we have in the stack, specifically the highly technical VRAM optimization guides.
Okay, yes.
These guides spend a massive amount of time talking about a newer, incredibly powerful model family called FLUX. They detail FLUX 0.1 LoRa's training extensively. So I had to challenge this setup. If FLUX is the shiny new toy, the supposedly superior next-generation architecture, why is this entire meticulous, beautiful Arynwood methodology built on the older SDXL model?
That tension between cutting-edge capability and actual usability is the central conflict of local AI development right now.
Really?
Yes. The choice of SDXL is not arbitrary. It is a calculated, strategic response to the physical hardware limitations of the people they actually want to use this technology.
So we have to talk about VRAM, video RAM.
We do.
This is the memory located physically on your computer's graphics card. And just for context, this isn't your system RAM like the 16 or 32 gigs you might have for opening Chrome tabs.
No, this is the ultra-fast memory dedicated entirely to processing graphics and, in this case, the colossal matrices of neural networks.
The sources provide a VRAM first breakdown of the landscape, and they identify 12 gigabytes of VRAM as the crucial threshold. They label it the budget home tier.
Which is highly accurate. If you are sitting at home right now with a standard upper mid-range gaming PC, you likely have a graphics card with about 12 GB of VRAM.
Like an RTX 3060, for example.
Exactly. You don't have a massive data center GPU, and you probably don't have a $2,000 flagship card with 24 GB of VRAM. 12 GB is the realistic reality for a hobbyist, an independent artist, or a student researcher.
And at that specific 12 GB constraint, the optimization guide is definitive. SDXL is the practical, comfortable choice.
The SDXL architecture can be optimized to train a LoRA within a 12 GB envelope reliably and consistently.
Whereas trying to train FLUX on that same 12 GB card sounds like an absolute nightmare.
It is a fundamentally different class of hardware requirement. The architectural difference is stark.
How so?
FLUX utilizes a transformer-based architecture. This is much closer to the architecture driving large language models like the text bots you interact with. The FLUX dev model contains approximately 12 billion parameters.
12 billion params.
It's massive.
The sheer size of the mathematical matrices required to hold 12 billion weights in active memory is staggering. At full standard mathematical precision, running FLUX is a 24 GB class experience, minimum.
Attempting to force a 12 billion parameter transformer model through a 12 GB VRAM bottleneck pushes the hardware to its absolute breaking point.
The sources list the hoops you have to jump through to make FLUX work on 12 GB, and honestly, it involves severe compromises. They mention requiring FP8 base quantization.
Yes.
Let's break down quantization, because it is a fascinating piece of optimization math.
Quantization is the process of compressing the mathematical precision of the model to shrink its physical file size in the VRAM.
So if standard AI models operate using 32-bit floating point numbers, which allows for incredibly long decimals and massive precision quantizing down to 8-bit or FP8, means you are literally chopping off the end of the decimals.
You are rounding off the math.
It's like having a hyper-precise painter's palette with a million subtly different shades of blue and throwing it away to use a standard 8-pack of crayons.
That's a good way to visualize it.
You save a ton of space in your backpack, but you lose the ability to paint subtle gradients.
The rounding errors accumulate. You lose stylistic nuance, and quantization is just the first compromise.
There's more.
Oh, yeah. The guide details that FLUX on 12 GB also requires aggressive latent and text encoder caching to the system RAM, which slows down the process immensely.
Because system RAM is slower than VRAM.
Exactly. You also have to drop your maximum training resolution down from 10,024 pixels to 768 pixels, degrading the visual quality. And you must use the Artifactor optimizer with a fused backward pass just to save every possible megabyte of memory.
It sounds incredibly fragile. The guide literally labels full precision FLUX training on a 12 GB card as not realistic and too large for a normal 12 GB setup.
Because it is.
Even with all those intense quantization tricks, they call it an advanced optimization project. You spend more time fighting your computer than you do refining your art.
It's like trying to cram a grand piano into the trunk of a compact car. You have to take the piano apart just to make it fit, and by the time you do, it doesn't sound right anymore.
That's brilliant. Now compare that architectural friction to SDXL. I mean, SDXL is like packing a well-organized suitcase for a trip. It's still a large model, but its architecture is inherently different. It relies on a UNet structure.
Right, a UNet.
A UNet is essentially the core engine of a diffusion model. Its job is to take an image that is completely destroyed by static noise and mathematically predict how to remove that noise, step by step, until a clear image forms.
And the SDXL UNet is massive compared to older models, about 2.6 billion parameters, but it is still a fraction of the size of the FLUX transformer.
2.6 billion versus 12 billion, yeah, big difference.
Huge. The SDXL architecture also employs dual text encoders, a CUIP, VITL, and an OpenSLEMUP Big G, which concatenate their outputs to understand the text prompt.
Okay, so it reads the text better.
Right. It utilizes size conditioning embeddings, meaning you feed additional mathematical vectors into the UNet, telling it the original size and target crop of the image.
It's a complex system, but crucially, the ecosystem around SDXL is mature. We have spent years figuring out how to optimize it.
We know how to tame it. The guide outlines the standard SDXL 12 GB optimization. You use a batch size of 1, utilizing an Atom 8-bit optimizer.
Atom 8-bit.
You engage gradient checkpointing to discard intermediate activations during the forward pass and recalculate them during the backward pass.
Wait, let me unpack that Atom 8-bit optimizer and gradient checkpointing, because that is the secret sauce. Atom 8-bit is the steering wheel we talked about earlier, but like quantization, it's operating with 8-bit math to save VRAM.
Exact.
And gradient checkpointing is just brilliant. Instead of the AI keeping all of its scratchpad math in the fast VRAM memory while it figures out how to adjust its weights,
It throws it away.
it throws the scratchpad math away to save space and just rapidly recalculates it when it needs it a fraction of a second later. It trades a tiny bit of processing speed for a massive saving in VRAM.
Through these mature, stable optimizations, you can train an SDXL LoRA on a 12 GB card at the full native 1024 pixel resolution. It is a lean, reliable loop.
So bringing this back to Lorelei Noble and the Arynwood project, their stated goal is digital hybridization. They want this to be a citable research artifact, right? And an evolutionary digital paintbrush that other people can actually use.
Yes.
If they built this exclusively on the FLUX architecture, they would be locking their entire methodology behind a 24 gigabyte hardware paywall.
They would be alienating the vast majority of the independent community. By consciously choosing SDXL, Arynwood Technology ensures their workflow is actually replicable on consumer hardware.
They prioritize accessibility and consistent iteration speed over chasing the absolute bleeding-edge resource-heavy model.
As the source material plainly states, if your goal is to train comfortably and iterate often, SDXL is the victor at the 12 GB threshold.
Which highlights a fascinating reality about how technology is actually adopted. The tool that wins isn't always the most powerful one on paper. It's the one you could actually run in your own home without your computer crashing.
Accessibility is adoption.
And because they chose an accessible, deeply standardized architecture like SDXL, they unlocked what I think is the most powerful feature of this entire project.
Ecosystem portability.
Yes, ecosystem portability. Let's talk about it.
It is the core finding of their research artifact. The output of this entire process, the Aaronwood LoRA, which compiles into a single file format called .safetensors, can transfer seamlessly between different SDXL derivatives.
Without requiring a new training session.
Exactly.
Let's break down why that is essentially digital magic. The .safetensors format is just a secure way to package the mathematical weights of the LoRa, right?
Sorry.
You've trained this lightweight study guide once, and the research proves you can just plug it into completely different brains as long as they share the SDXL architecture.
Because the open source community rarely uses the vanilla foundational SDXL model released by the original developers.
Nobody uses the base model.
Thousands of independent developers have taken that base model and fine-tuned it in radically different directions. These are called derivatives or checkpoints. Some are tuned for photorealism, some for anime, some for architectural rendering.
The Arynwood research tests the portability of their LoRa across these different brains using an interoperability matrix.
It's a great test case.
They highlight two specific examples that demonstrate the immense flexibility of this workflow. First, they establish a base environment using a checkpoint called Juggernaut XL.
Juggernaut XL is a highly refined photorealistic derivative. In the matrix, Juggernaut holds a native portability status.
So what does that mean when you apply the LoRa?
When the Arynwood.safetensors LoRa is applied to the Juggernaut unit, the generation is high fidelity. The model perfectly interpolates the subtle pastel mutations and the specific color variants of the original 48 Procreate drawings. The translation is flawless.
But then they take that exact same LoRa file, no retraining, no adjustments, just the same 32 rank math file, and they drop it into a completely different checkpoint. DreamShaper XL Turbo. This is the transfer target.
DreamShaper XL Turbo is a fundamentally different derivative. The turbo designation means the architecture has been distilled to generate images in far fewer steps.
It's built for speed.
Right, and it inherently possesses a different, often more stylized aesthetic baseline than Juggernaut.
But the transfer is still successful. The matrix notes that while DreamShaper generates fuzzier, inherently more artistic outputs due to its lower step count, it crucially maintains the core stylistic identity of the Arynwood tag.
The subject identity, the DNA of the artist, survives the transfer into a totally new neural environment.
And this structural flexibility is what powers the most impressive feature of the Arynwood Design Studio front end.
The Bring Your Own Model, or BYM, workflow.
The BYM workflow is a masterclass in user experience.
It really is.
The React interface allows the end user to bring whatever base checkpoint they prefer, whether it's Juggernaut, DreamShaper, or a custom model they downloaded today, and dynamically combine it with the trained LoRa's on the fly.
The interface conceptualizes these LoRa's as dynamic-style chips.
I love that visualization. You have your base model loaded, which contains the vast world knowledge of anatomy, lighting, and physics, and then you just click on a chip that says Sage Sketch, or Graphite Noir, or Aaronwood.
Instantly, the math from the LoRa injects into the unit.
You are completely decoupling the artistic style from the foundational knowledge of the AI. You can inject Noble's 100 hours of pastel brushstrokes into a hyper-realistic photograph engine or a fast-rendering animation engine instantaneously.
The value of this decoupled workflow for the community is immense. It empowers the end user to experiment endlessly with cross-pollination without incurring the massive computational cost of retraining a new LoRa for every single aesthetic combination.
It turns a static research dataset into a truly alive, flexible tool.
Absolutely.
Now, hearing how seamlessly this works across all these SDXL derivatives, a logical question arises. What happens if someone tries to plug this highly refined, perfectly structured Arynwood LoRa into an older architecture?
Like SD 1.5.
Yeah. What if I take this .safetensors file and drop it into the classic Stable Diffusion 1.5 model, the model that basically started the open source AI art craze. Does the image just look a bit worse? Does the Arynwood style just get slightly diluted?
This brings us to a fundamental lesson about the physical structure of neural networks. The answer is no, it doesn't just look worse. Attempting that transfer results in a catastrophic failure.
Catastrophic. The sources document this explicitly as the SD 1.5 architectural barrier.
It's a hard stop.
When the SDXL-trained Arynwood LoRA is applied to an SD 1.5 baseline checkpoint, it yields a completely generic generation with zero stylistic influence. The model ignores the carefully crafted Arynwood-style tags entirely. It's as if the LoRA doesn't exist.
To understand the mechanics of this failure, we have to look at the mathematical shape of the data. We have to talk about tensors.
Let's ground the concept of a tensor for everyone. A tensor is essentially a multi-dimensional array of numbers. It is the physical mathematical shape of the data as it flows through the layers of the neural network.
Right. And the tensor structures optimized for the SDXL architecture are vastly fundamentally different from the structures in SD 1.5.
Because SDXL operates natively at a 1024 by 1024 pixel resolution, its internal mathematical layers have a specific width and depth to handle that density of information.
SD 1.5 operates at a much smaller 512 by 512 resolution.
Furthermore, as we established, SDXL uses that complex dual text encoder system, meaning the text prompt is processed into a tensor shape that SD 1.5, which only has one basic text encoder, cannot even begin to read.
The mathematical shape of the Arynwood LoRA is explicitly designed to lock into the specific high-dimensional architecture of the SDXL UNet. When you attempt to plug those weights into SD 1.5, there's a literal structural incompatibility.
It's like trying to play a PS5 game disc on a PlayStation 1.
Oh, that's perfect.
The console doesn't just play it with worse graphics. It simply doesn't recognize the disc at all and defaults to its home screen.
Exactly. Or, trying to snap a massive Lego piece with 1,000 connection pegs onto a base plate that only has 500 pegs, spaced completely differently, you cannot physically force the math to align.
It doesn't matter how hard you push.
Right. The matrix multiplication required to apply the LoRa weights simply cannot execute. The dimensions do not match.
So what happens? Does the computer crash?
To prevent the entire software application from crashing, the system is designed to gracefully fail. It drops the incompatible LoRa weights entirely, bypassing the fine-tune completely, and executes the generation using only the base SD 1.5 knowledge.
Which is why you get a generic image. The base model just ignores the 1024 peg Lego block because it has nowhere to put it. But what's fascinating to me is that the sources do not frame this architectural barrier as a bug or a flaw in the project.
No. The research explicitly frames this failure as a successful proof of concept.
The absolute inability to transfer the style backward to an older model proves just how deeply the Arynwood LoRa is leveraging the advanced complexity of the SDXL latent space.
It's validating their methods.
Right. It proves that the nuanced stylistic data Lorelei Noble captured all those pastel mutations and specific brushstrokes organized in Stage 3 requires the massive 2.6 billion parameter UNet to even exist mathematically. It validates the entire methodological choice to use SDXL.
It confirms that the data discipline worked. The style is so highly dimensional that a smaller network physically cannot hold it.
So having mapped this entire technical journey, from the hundreds of hours of manual Procreate strokes in Stage 1, through the friction of the machine vision auto-captioning, into the rigorous structural tagging using the Arynwood anchor in Stage 3, and then navigating the hardware realities of 12 GB VRAM optimization and tensor incompatibility, we finally get to zoom out.
The big picture.
Yeah. We need to look at how all of this intense back-end math is actually presented to the human being sitting at the computer, and the ultimate philosophical conclusion of the research.
We touched on the Arynwood Design Studio's React interface earlier, but let's examine its front-end infrastructure in totality. As a local-first application, its primary function is to abstract the technical friction away from the artist.
Local first is a critical distinction today. Your data, your 48 deeply personal images, are not being uploaded to a massive corporate cloud server to be scraped or analyzed.
Privacy is built in.
The entire FastAPI router, the Squalid database, the Koya SS training queue, it is all happening on the silicon inside your own machine, entirely under your control.
The architecture prioritizes data sovereignty, and the UI design is relentlessly focused on seamless transitions. It features drag-and-drop training.
I love that. A user literally drops their source photos onto the canvas, and the front end automatically triggers the complex data prep, initiating the WD-14 captioning we discussed, without the user ever opening a command line terminal.
Then you have the BYM workflow with the dynamic style chips for immediate generation. But it goes further. The studio features an integrated editing suite directly on the canvas.
So it centralizes the workflow. You can generate an image using the Arynwood LoRA and then immediately utilize utility features like magic erase, automated background removal, custom filtering, and unlimited layering.
All without exporting the image to Photoshop and breaking the creative flow.
The user experience design here is just a monumental achievement in abstraction. They have taken the massive, fragile complexity of tensor mathematics, gradient checkpointing, and adamant bit optimizers, and they have hidden all of it behind a seamless drag-and-drop React interface. The artist just feels the magic of the tool. They don't have to calculate the math.
It is the distillation of a complex formula. The project demonstrates that thousands of developer hours spent writing back-end Python code, combined with hundreds of brushstroke hours in Procreate, results in a valid, current digital art tool.
And crucially, Arynwood Technology is not keeping this formula a secret.
No, the open availability of this infrastructure is a core pillar of their research.
They have published the research methodologies on Zenodo and OpenAir, securing a dedicated DOI to make it a fully citable academic artifact.
The source code for the interface, the specific training scripts, and the models themselves are publicly available on GitHub.
And it is all released under a Creative Commons 4.0 license, specifically CC BY 4.0.
A license designed explicitly to foster community collaboration and adaptation.
Lorelei Noble and her team are not hoarding this digital DNA. They aren't wrapping it in proprietary DRM or locking it behind a monthly subscription fee.
They want people to use it.
They're giving the architecture away so the independent community can dissect the matrix math, learn how to build their own structured data sets, and build upon the methodology. It embodies the absolute best spirit of open scientific and artistic research.
This methodological approach actively redefines the prevailing narrative surrounding AI and art. In this highly disciplined, self-trained, local-first context, the technology is not an engine of replacement. It is an engine of hybridization.
Which brings us to the quote from Lorelei Noble that perfectly anchors the synthesis of this deep dive.
It's a great quote.
Reflecting on the entire process of feeding her art into the SDXL architecture, she says, "The AI does not erase the artist. It acts as a mirror. The generated output is the software's unique interpretation of a human's painstakingly developed manual technique."
And she concludes with,
"This is my computer telling me what it thinks my art represents, and I'll take it as a compliment."
the machine is reframed not as a competitor, but as an incredibly fast, profoundly literal student, holding a high-dimensional mirror up to the teacher's aesthetic.
It has been a deeply technical and wildly fascinating journey today. We started with the subjective, analog strokes in Procreate, navigated the literalist trap of automated machine vision tagging, and learned how rigorous data discipline, specifically carving out an empty mathematical coordinate using the Aaronwood anchor, saved the stylistic soul of the project.
We unpacked exactly why the physical limitations of 12 GB hardware dictated the use of the SDXL UNet over the FLUX transformer.
Right, and how that strategic choice unlocked a seamless, portable BYM front end that empowers the entire open source community.
We have mapped the exact architecture where human intent and tensor mathematics successfully integrate to create a new kind of citable hybrid artifact.
It fundamentally changes how you look at the data you produce every day.
Yeah.
And I want to leave you with this final lingering thought.
Okay.
If you were to gather 100 hours of your own deeply personal creative labor, whether that is your writing, your coding, your photography, or your painting, and you meticulously curated it, maintaining perfect data discipline to train a local AI strictly on your own output, when that machine finally compiles the math and holds a mirror up to your life's work, what hidden patterns about yourself do you think you would see?
Wow.
Would you recognize the aesthetic coordinates of your own mind? Or would you find yourself staring into a high-dimensional reflection you never expected? Thank you for joining this deep dive. Keep exploring, keep questioning, and keep an eye on that beautiful, complex intersection where humanity meets the machine.